Good morning, class. We should start with today's thing. Today's lecture is slightly different. The plan for today is not to cover any new material, but I'm planning to essentially do a review of what we've seen so far, and talk a bit about experimental practice and how you might go about setting up experiments in machine learning and such things. And I would like this to be a more interactive thing. And I noticed that there are, on an average, at least 50 of you in class, and I would like to see more of you asking questions. So I would like to make this a little bit more interactive today. But before we get into the review and such things, I want to just remind you of a few things. There's a project milestone that's due today. The idea is that you should have at least one non-dummy submission on Kaggle. The dummy submission was what you did for the previous checkpoint, where you just uploaded a file that we gave you. This time, your submission should contain the predictions of some algorithm. Um, in addition to submitting things on Kaggle, you also need to submit a short report, no more than one page, that describes what you did so far. When I checked last night, the top score on Kaggle was 84. Maybe it's gone up a bit now. I don't know. Um, and one request I have for all of you is when you do submit on Kaggle, I think it allows you to add a comment that describes what your submission contains. Use the comment field to it's like your commit message for a repository, for example. Use that comment to describe what algorithm that submission represents and any choices that you may have made with features and such things. The reason is as we go along, you'll see that there will be, you're required to do at least 6 submissions by the end of the semester. And some of you do a lot more. So at the end of the semester, I'll ask you to pick 6 submissions that you want to be treated as your official ones. And I would like to know when at the end of the semester, when I'm grading, to know which submissions correspond to which algorithms, for example. So it would be nice if you could just make uh, uh, my life a little bit easier. And then there's another question, which is um, there's another the reminder about homework 4. It's on Canvas. It's due October 29th. Of course, you get an extra day for late day for everything, including the project milestone, with a 10% penalty. The homework 4 talks about learning theory. We've covered all the material we need for homework 4, but I encourage you to start early if you haven't started already, because this is the topic that most people have told me is tricky. And this is the homework in general, irrespective of what the questions are, that a lot of people find a bit sort of time consuming, not in terms of effort, but in terms of just thinking through the answers. It's not brute force effort like running your code, but just you have to understand the concepts. So please do start early. There are a few questions, so let me get to that. So there's a question in the homework. Uh, it asks, give an example of a finite class that has um, a VC dimension of exactly log of size of the concept class. Um, the question is, doesn't this give us an opportunity to be super cheap and pick an easy example? So those of you who've not seen it, this is the third section, VC dimension, and this is question 3C. Um, it's not enough that you just tell us a concept class. You need to prove that the VC dimension is log of is that amount. So you can't just say, okay, here's a class. You need to remember that the general rule for this homework at the top is we need an explanation. In fact, if you do not give an explanation, we reserve the right to not give you any points. So you need to not just say, here's a finite class with blah, blah, blah. You need to also show, so that means it requires a VC dimension proof. And if you can pick an easy example, good for you. I mean, of course, I don't know what specific easy example you have in mind. So if it is something trivial that, like for instance, um, if your class of functions is empty, I'm not going to allow that, for instance. So, I understand the spirit of the question. So if you're asking the question, I would expect you to understand the spirit of the question, so and take it accordingly. If you're asking the question that you asked on the chat. So another question is, how would you grade the milestone? Is there a certain range we should be at to get full credit? No. For this particular milestone, my goal is that you get the work done. So I want you to have a workflow set up. The goal of this milestone is to ensure that the next milestone gets easier. The next milestone will require you to have two more submissions. So in some sense, the job of all these milestones is to make sure that at the end of the semester, you don't try to do your project in one day. So that way, if you kind of do a little bit of the project every month, you are basically done. So I need you to submit, make a submission. That said, though, I expect pretty much every, not every, but any reasonable learning algorithm should be, for example, better than the majority baseline. So you need to know what the majority baseline is. And any reasonable method should be more than the majority baseline. Otherwise, I will probably penalize a bit. Otherwise, I'm going to be rather flexible with this particular milestone with respect to the what do you call it, the performance in terms of accuracy. In the project, there's another question. Can we combine average decaying rate and margin perceptron and use it as a classification algorithm? You can, but all of these would count as perceptron. I would be surprised if they do much better than the average perceptron. So I am not entirely, remember that you're required to do a certain number of runs and a certain number of different algorithms, and all of these would just count as the perceptron family. There are a lot of things on the homework that I can intuit, but I don't know how to show it. What should I be doing there? Ben, if you have any specific questions, I can answer that. But in general, so let me just kind of give you a few examples. So the VC dimension and shattering questions tend to give people the most amount of grief. In particular, as you know, you might notice as the homework goes on, the VC dimension questions become more and more terse. It just says, show that the VC dimension is this. In general, let me maybe talk about this. So every VC dimension proof, so if I want to show that the VC dimension of some concept class is some number n, every VC dimension proof typically consists of two parts. There is one part that shows VC dimension of the concept class is greater than equal to n. And then the second part that shows the VC dimension is strictly less than n plus 1. So every proof for VC dimension has to have these two parts. What does it mean to say that the VC dimension is greater than equal to n? Essentially, what I'm asking you for the VC dimension proof is to step through the definition, really. So this means there exists n examples such that for so let me walk through this. So this is all I've done is this is just the definition of shattering. This is saying that the set can shatter some set of n examples. So in the VC dimension proof, what you need to do, this is really the harder, I mean, this might be a somewhat tricky thing. You need to just show that there exists a set. There are many ways of showing that a set exists. As far as this class is concerned, all the proofs that you will do, you need to show that it exists by constructing the set. So this is where you need to be a little bit creative. Think about the class of functions. So all you need is for one set of functions. So in the axis aligned rectangles in 2 dimensions, it says VC dimension, show that the VC dimension is 4. You need to show 4 points. Think about an arrangement of 4 points in the 2D plane such that no matter how those 4 points are labeled, you have 4 points, which means you have, all of them are plus, all of them are minus, some of them are pluses and some of them are minuses and so on. No matter how they are labeled, there is a certain function. So you need to prove this. Irrespective of how the labeling is, you need to find a function inside the set of functions we consider, the C, that will also make the same predictions. So in the axis aligned rectangle case, for instance, you would have to, no matter what labeling there is, you need to produce a rectangle that also would produce the same labeling. So this is, this part might require a little bit of thinking, especially the construction of the set and proving this thing. So you can, the way to prove this could be through enumeration. You could enumerate every possible labeling of those 4 points and say, okay, if this is the labeling, this is the function. If this is the labeling, this is the function, and so on. Or you can make a more general argument. When you want to say that the VC dimension is strictly less than n+1, this is really the inverse of this statement. So that means this statement has to be false for n+1, which means for every set with n+1 points or examples, there is some labeling such that no function in C matches it. So that means that, you need to find, this tends to be the harder part of the proof typically. The first part, the confusing, in the first section, the confusing part is this thing here. In the second part, the confusing part tends to be, how do you show it for every set with n+1 points? So in the axis parallel rectangle case, if I want to show that the VC dimension is 4, you need to show that no matter how 5 points are arranged on the plane, you need to construct a labeling of those 5 points such that the set of functions don't match it. So in some sense, the proofs for VC dimension all have the same template, and you need to kind of be careful that you respect the quantifiers. So you have an existential quantifier here, and you have a universal quantifier here, and this is just some function, which means it's an existence. On the other side, you have an existence here. This is every, so universal. This is some function, which is just existence, and this is no, so it's a universal. So this tends to get complicated. My recommendation would be, write down something like this and make sure that you step through the process. It's a very mechanical process. It's much less harder than you might imagine, but a lot more tedious. So you just need, but the general answer, going back to the thing, if you have specific questions, you need to, feel free to use the chat or come to office hours. But in general, we want you to kind of think about the definitions of each of these things. Like, when I say VC dimension, if I say show that for some finite hypothesis class, the VC dimension is at most log C, then think about the definition of VC dimension and shattering, and use the other thing to think about is when you are kind of inventing the proof, come up with a small example. Don't think in the abstract. Think in the concrete. Come up with one or two small examples. Maybe a hypothesis class with 4 functions, or a instance space with maybe 4 examples, or dimensionality is 2, and so on. And try to get an intuition of what the argument is and generalize that beyond. There's another question. Again, going back to the project, how many submissions should we have by the next milestone? You need to, all of this is listed in the projects page of Canvas. But for the next milestone, you need to have 2 more submissions. How do you tell whether we used a different learning algorithm for each of the submission? I'm assuming that you're going to describe that at the end of the semester when you actually do the final project report. You'll also have to submit your code, and you'll have to update you on Kaggle. I want you to annotate your submission with a comment or something that describes which algorithm you use. So to clarify, another question, to clarify something about the project, say we use the perceptron with a certain set of features. If we create our own set of features and run perceptron on it, would this count as 2 unique submissions, or do the learning algorithms need to be distinct? Yes. So let me remind you, for the project, you need at least 4 different algorithms, at least 2. I mean, this is by the end of the semester. Different feature representations, and at most 1 submission that uses a library, and 6 submissions in all. So if you use perceptron with a certain set of features, then you've used up 1 algorithm. And if you run it with another set of features, you've used up 2 feature sets already. So you've checked this box. You can't, your official submissions will not be, you can't, I mean, your official 6 will not, you can't use any more features. I mean, you can try more and you can change your official 6 at the end of the semester. Oh, there's a clarification at the end. The dummy submission does not count. 6 submissions in addition to dummy. And that's important. So Michael, to answer your question, in theory, these would count as 2 unique submissions, but you would have used up the feature box. And you can imagine there's like a lot of flexibility that you have here. You can use different kinds of learning algorithms with that we'll encounter in class and you'll implement in your homeworks, but you can also play with other ideas. For the project, what happens if we combine more than 1 algorithm? Say we use perceptron and decision tree together to maximize the score. So this is a more general idea that we'll be encountering sometime soon, called ensembling. The idea would be you have not 1 classifier, but a committee of classifiers, and they together somehow, or together they make a different classifier. So ensembles, I'm going to treat as a different classifier, as a different submission. Let's see, there are more questions. By different feature representation, is that like bag of words and glove? Yes, it could be bag of words and glove are different feature representations, or you could do feature transformations, or you could invent your own features using the metadata. And in fact, I suspect at least some of the submissions that are close to the top of the leaderboard are using the metadata features, which in itself is an interesting thing to think about. Why does metadata about a case help us decide whether the case was, whether the person was charged, was pronounced guilty or not? It almost seems like it's a problematic thing. If you can tell whether a person was guilty or not based on their age, it seems a little weird. But I'll ask you to reflect on those things in your final project report also. But yes, for now, bag of words and glove are different features. Can we submit a library algorithm once all the other requirements are satisfied? And we count only one library submission? Yes, your final 6 can have only at most one library submission. Feel free to keep submitting library code. Bear in mind, you don't want to kind of brute force the thing and submit something that takes the accuracy up to 99% and end up demoralizing your friends in the class. But other than that, I have no idea whether this data set can go to 99%, but you feel free to make submissions. Only one of them will count. All right, so if there are no other questions, we've talked. Oh, there is one more question. The challenge with a lot of these questions is that they are very spatial. I can draw things out on a piece of paper, and then taking that idea and proving it in a brief, concise, concrete explanation becomes far more complicated. Obviously, including figures is an option, but this will take a lot of, this becomes impossible with d-dimensional things. Absolutely right. So I think you need to describe it in you can build your intuition using pictures, and that works in 2 dimensions. With 3 dimensions, of course, it's not going to work. And try I would encourage you to kind of think about how that intuition can be put into words, and I can help you out if you come to Office Hours, or one of our TAs can help you out. The thing is, with d-dimensional space, nobody knows how to plot it, or at least nobody knows how to plot it well. So the spatial intuition has to be written in words, unfortunately, or in algebra, or in symbols, in a way that is that a reader can understand. And this is the limitation that our own cognitive system has, and our media have. So we have to live with that. I would, while I do sympathize with you, because this is I feel that all the time. Forcing yourself to clarify that intuition in words goes a long way towards understanding what the underlying concept is. And personally, I find that to be very helpful. So, I encourage you to think along those lines. Okay, so what I'm going to do is, as I said, today's lecture is a slightly different one. Just for those of you who came in late, the reminders for today are the announcements or reminders are, there's a project milestone that's due today, and there's homework 4 on Canvas. So as I said in the beginning, today's lecture is a slightly different one. Instead of talking about any new material, I'm going to talk about stuff that we've covered so far, stuff that you may have seen, but maybe you missed, or maybe you didn't really internalize, or maybe you just didn't put it all together, or you just want to see it again. Essentially, I'm going to do a mid-semester review of everything that we've touched upon. And the point of this is I want you to kind of ask me questions about things that you are unsure about, or just make sure that you understand these things. Some of these ideas we won't revisit again in the semester, and some of these ideas will form the basis of what we are going to build up, get into. And in particular, we'll spend a lot of time talking about learning as optimization and such things. So let's get going. So the plan for today is a mid-semester review, and it's just where we are. The hope is we can use this to take stock of what we have seen so far. And please do ask questions. I mean, I can go through this in like 15 minutes, but that's not going to help anyone. So at the start of the semester, so for the entire semester so far, we've been looking at supervised learning. And the key concept that we've looked at, which underlies everything that we are building up is that learning is search over functions. This is a rather simple statement, but it's easy to forget that your decision tree, when you're writing your code, may not look like it may not remind you of a function. The perceptron does not remind you of a function, but really learning is search over functions. It's search over entire spaces of functions to find the best one, and we have to define best in different ways. When we're talking about supervised learning, we have this terminology or vocabulary that we've been using, uh, which includes the instance space. The instance space is the set of things that we want to classify or make a prediction about. Um, it may seem like the instance space is such an easy thing. You're given the instance space. When you're given the problem, you're given the instance space. But often deciding on the instance space can be tricky. And sometimes deciding on an instance space could give you some extra mileage that maybe you that give you an edge over someone else who's also applying machine learning. Let me give you an example. So let's say that your instance space consists of documents that you want to assign labels to, or images that you want to assign labels to. Now, at that point, it seems pretty obvious. The instance is an image and the label is whatever the label is. But you could expand the instance space. Instead of a single image, you can say the instances now consist of pairs of images or pairs of documents, and you want to kind of assign a joint label to them so that they both have the same label. And now you have more information to make your decision. May not work, but you have essentially kind of redefined the instances from the what you were given. As a machine learning engineer or a data scientist, a good part of what you might do might involve thinking about what is a good instance space and how do you best featureize it. There's also the label space. The label space defines what kind of problem we have. We can have classification, where the labels are discrete, binary classification, which has been our good friend for since August. It has only 2 labels. Regression is the case where the label space is a set of real numbers. Now, multi-class is when you have more than 2 labels. You can have combinations. You can predict graph valued objects. You can predict trees. You can predict programs. There is and such things. And essentially, what is changing here is the label space. The key notion here is that the instance space and the label space together decide the input and the output to your classifier. The function that we want to find, learning is search over functions. The function that we want to find is going to reside in the concept space. The concept space is this abstract thing. We don't have access to it. It's just an abstraction. We are imagining that nature has chosen its function from this set of functions. We don't know what it is. It's just something that it's worth giving a name to because we'll use that name later on. The actual concrete set of functions that we will search is called the hypothesis space. And the good part of machine learning, even today, these notions were first formally named in the 80s, let's say. But even today, a good part of applied machine learning involves inventing a hypothesis space, even though people may not even think about it that way. Today, you may have heard of a lot of neural networks and such things. Essentially, every time people say they have invented a new kind of a neural network, it is it often ends up being they have constructed a new hypothesis space that somehow seems to fit the problem better. This idea of knowing which functions you're searching over is a useful abstraction. There's a question for classification is a finite number of labels. Regression is a real number of labels. What is a real number? Regression is essentially, does regression require real number instance spaces? Not necessarily. You could have discrete inputs and try to predict continuous outputs. The regression, this distinction is entirely based on the labels. Okay, so the An important idea that we have seen in at least a few different ways so far, and we'll touch upon that again, is we need to restrict the hypothesis space. If we are going to search over every single function that exists, learning is a hopeless venture, because we will end up finding functions that also fit the noise in the data, or we may not even ever be able to understand, generalize beyond, because every data set can be perfectly explained by some function. Think polynomials, curve fitting. A large enough polynomial can fit any data set. So we need to restrict the hypothesis space, otherwise we might end up fitting the noise in the data. Another clarification: regression is continuous labels and classification is discrete labels. That's correct. So what are the general issues you need to think about when you're applying supervised learning? And you need to think about what kind of hypothesis space you're using. This is often an implicit choice. If you, for example, use the perceptron algorithm and don't change the features, you're implicitly committing to using a linear classifier. If you use a decision tree and say that I'm going to do a depth limited decision tree, you're implicitly choosing to use a certain set of functions. So, and we'll see as we go along, when we use these various named algorithms, we are implicitly using certain hypothesis spaces. And this is not just like an abstract, these general issues that we need to consider. They're not just abstract choices that are useful for proving theorems. These are practical issues. You need to know what classifier you're going to use if you're going to actually use a classifier. Another issue that's worth thinking about is what are good features, or what is the representation that is used for building models. Now, this is an open question. This, a good representation is a perfect representation will make your learning problem trivial. But how do we know whether a representation is perfect? So that takes us to two different directions. On one hand, we could say, I'm going to use insight about the problem. I'm going to think hard about the problem, come up with the best features using everything that we know, and we're going to use that. And that's roughly the kind of setup that we've had in the class so far, even for your homeworks and so on, and your project even. There is some feature set that's given to you, and you're using that. On top of that, you can do interesting things like expanding the features, concatenating them, or combining them in some way to kind of get more out of the data that you already have. All of this is one direction. The other way is to say, there is no way I'm going to figure out what are good features. Let me use some simple features and then convert this problem of finding a representation that best describes my task into a learning problem. So I'm going to simultaneously learn a representation and the classifier that works with it. Now, this seems like a rather difficult task, and it is. This typically invariably leads to optimization problems that are hard to solve, and this is the fundamental basis that underlies modern neural networks and deep learning. As you may have heard of deep learning and neural networks. Another name for the same field could be machine learning with learned representations. It's not as catchy a name, so it's never going to get used. Yeah, that said, though, one of the big conferences for deep learning is called the International Conference on Learning Representations. So the idea of knowing which features are important is an open question, and it involves any insight that you can throw into the problem. As an example, I've had former students and current students who are interns in various places tell me that they spent a good part of their internship essentially feature engineering, because machine learning by itself is easy. You may or may not agree with that, but it's easy because you just, as you will see, there's like a unification of a lot of ideas. But we don't know what features are going to be helpful for the next task. So you spend a lot of time inventing features. Once you have that, you have to decide which learning algorithm you're using. I'm not going to spend too much time talking about that because that's going to be basically all of everything the rest of the thing. So one of the first things that we saw, by the way, feel free to ask questions. I'm also hoping that this is an opportunity for people who don't usually get to ask questions to participate, because we are revisiting things that we've seen. And I do want, if this was a real class, I would force people from different physical sections of the class to actually ask me questions. But now I can't do that because I don't know where you are. But please do ask questions if you've not participated before. What do I mean by feature engineering? Feature engineering is the task of inventing features and coming up with good features, basically. Isn't the number of samples in a training set another issue? Yes, it is. It's a very big issue, and for better or worse, we often don't get to control it. I mean, in an ideal world, we would like to control the whole process by creating the training set. But sometimes we may not have the luxury of constructing a training set, and we will have to live with the number of examples that we have. Right. So let's talk about decision trees. So you need to know what decision trees are. It's a hierarchical data structure that can represent data. And you need to know what kind of functions they represent, and a rough estimate of counting of how many decision trees there are. In fact, if you think about it, this is really a question that's in your homework. How many decision trees are there with certain depth? This is also a cause for confusion for several people. The number of decision trees can, it changes based on the definition of what you mean by counting decision trees. Let me give you an example. So let's say you have a tree. I'm going to draw just a random tree here. Let's say you have two features, A and B. Let's say this is true, and here it's false. And let's say here also it's false. But this tree is kind of lame. I mean, it says you check, let's say this is, when A is 0, you predict true. Otherwise, you check B. If B is 1, you predict false. And if B is 0, you predict false. This is exactly the same as this tree here. You need not have constructed it. So this is the difference between these two trees that I have drawn on the slide are functionally equivalent. They are identical because they produce the same output. They are structurally different. And clearly, the number of structurally different trees is much more than the number of functionally different trees. Because these two things represent the same function, but they are two structurally they look different. In fact, another structurally different tree is the mirror image of this thing. If I put a mirror here and just flip the tree, you'll get a different looking tree. So when you're counting trees, you have to be careful how many decision trees there are. For the homework, just consider structurally different trees. So there's a question: is there a better way to spend more time making the feature engineering? Okay, this is an interesting question. Is the better way to spend more time making the feature space better, or trying a lot of different algorithms? I believe that, by the way, what you're going to hear is just my personal bias. It may not be the truth. I believe that the amount of time you spend with better feature space is probably better. Because improving the feature space introduces new information into the system. Typically, we will see, for example, average perceptron, support vector machines, logistic regression, and such things are essentially the same. They are very, very similar to each other. They have very different intellectual lineages, but they behave very similarly to each other if you give them the same set of features. But if you add extra information into the system, most learning algorithms learn to pick it up. So I think, I mean, again, as I said, this is a personal bias that just comes from having used these algorithms before. Um, most of the times, these things tend to perform very similarly. So in practice, I would suggest spending time on feature engineering. But that said, in order to do feature engineering, you need to understand what the algorithms do, which is why the class is still not futile. Um, and the other thing that we will see when we talk about learning as optimization is from an optimization point of view, once we start framing learning as from the looking at learning, the process of learning from the lens of optimization, a lot of learning algorithms look very similar. In fact, this is like uh, the big insight that came into existence actually in the 1970s. It was revived in the 1980s, kind of went into the background in the 90s and early 2000s, and then came back in a big way in this decade, which is this notion of mechanizing learning. You don't write down a new learning algorithm every time you want to do something. What you do is you write an algorithm that creates your learning algorithm. We will see this because in a certain manner of speaking, that's what backpropagation does. So we can mechanize learning quite a bit, and so a lot of insight goes into feature engineering. There are a couple of related questions. So can I list those learning algorithms that behave very similarly? Average perceptron, support vector machines, and logistic regression. And we'll encounter all of these. Our next thing that we'll see is support vector machines. Are there any additional reading? Is there any additional reading on feature engineering that I recommend? Frankly, I think feature engineering requires a lot of thinking about the problem. It can end up being a very a highly domain dependent thing or a task dependent thing. The insights that may work, for example, for deciding whether to buy or sell a stock are probably going to be very different from the insights that might work for, say, um, deciding whether a certain segment of a gene is a marker for Alzheimer's. It may not really necessarily be um, there may not be one um simple strategy that's going to always work. Instead, what I would recommend for feature engineering is understand what your algorithms do with those features. Understand what will happen if you give extra features to the algorithms. For instance, here is an insight that has helped me at least for in one research paper. So we were working on a task and we threw every feature that we could think about at it, and the improvements that we observed were kind of minor and not something stellar. And one of the things that over discussions that we realized is the features that we have are, so the task involved predicting, just as an example, you have a graph, you have two edges, and we had to predict the relationship between them. We had to predict a label here on the edge. And we realized that the features that we had were all features from either A, I'm going to write phi of A, or features from B. There was no element in the feature space that actually combined both of these things. So all we did was essentially took the features of A, took the features of B, and did this quadratic transformation. And suddenly the numbers jumped up. This was an insight that came from the observation that we are predicting a label on an edge, which means we need the learner or the classifier to actually see terms that combine these two nodes. You can't just have A and B separately, you need to combine them. And like I said, this is just, the idea of feature space expansion has, I have found it to be useful quite a bit. And things like that, adding a bias feature. So understand what your learning algorithms will do with those features if you provide them, and that could be helpful for feature engineering. There was another question that I missed. We didn't cover regression trees. Can I give an example? We didn't cover regression trees. In fact, we didn't cover a lot of material. Frankly speaking, I always feel regret about this class because of all the stuff that I don't get to tell you about. A regression tree could be something like where instead of predicting, say, labels at the end, at the leaves, you could have functions. Various various different functions, each of which produce a real number, and the tree is selecting which function do we pick. So we have and each of these is not just a function of its own, it could be a learned function. So for example, imagine that this was W1 transpose X, and this is W2 transpose X, and this is W3 transpose X. 3 feature vectors, 3 perceptrons, and the tree decides which one you pick. And this could be an example of a regression tree, where we have a tree and also a set of functions at the end that make predictions. They don't have to be functions, they could be numbers, for instance. Do I recommend reading the Master Algorithm by Pedro Domingos? Do you have any comments on it? I haven't read it myself, so I don't know. If one of you reads it after the semester, let me know what you think. Can you mention the paper about the link prediction? It's not a very important thing. I mean, it's kind of orthogonal to what we are doing. So you can send me an email, I'll send you a link. Okay, so let's go back to decision trees. One thing you need to know about is how do you deal with continuous features? Sometimes the feature space might not be discrete, but the decision tree requires discrete things. A can either you have to have a countable number of outcomes here. So if A is a real number, you can't have a branch coming out of A for every possible value of A. So the standard approach is to bucket the features. All of this said, of course, you also need to know how to predict the decision tree and understand that given a single data set, there are many, many decision trees that can represent it. And that takes us to the learning algorithm. ID3 is a greedy heuristic that finds one of the many decision trees that represents the data set. It's a very simple algorithm. It's one of the it's simple in the sense that it's easy to describe. Essentially, all it says is if it observes that creating a tree requires you to pick a root and talk about what happens for each value that the root can take. Each node is a test. So if you have the feature A, if A is A1, A2, and so on. But the insight here is that once you've done that, underneath this, you still have a tree. So all you need to do is pick the root and then start creating these branches. And you need to construct a tree. We can make a recursive call to ID3. Only this time, we don't get to use the feature A anymore. We can't, and all the examples that we are using, sending down this path, all of them have the value of A1 for the feature A. And we make a recursive call. So, and there's a base case. The base case is if we have run out of examples, or if we have run out of, at any point, if we need to stop because all the examples have the same label, or because we've reached the depth limit, or we've run out of features, then we create a leaf with a label. The key trick here, or the most important part of this whole thing, is how do you find the root? And for this, we saw the information gain heuristic. It's a heuristic. The information gain heuristic tends to help, and it tends to kind of favor shorter trees. It's not guaranteed to produce the shortest tree, but it favors shorter trees. The information gain heuristic is built on the notion of entropy, and we saw many different variants of this entropy-based measure that you should be comfortable with. Another question about features, adding more features. So did I say that adding more features doesn't help, but combining them might improve? No, not quite. Adding features can also help. So interestingly, with features, there are 3 things that can help. Could help. I'm not saying will. Adding features could help if you add the right features. Combining features could help if you combine them the right way. Removing features can also help if those features are just noisy. So this is why feature engineering is a little bit tricky, because any operation you perform to the feature set might help, but you have to think about why. There are heuristics. If someone sends a message on in a discussion board, I can send a pointer. There are heuristics for feature engineering that involve pruning the set of features and finding the best set given a large superset. The short answer is they don't. They are all computationally heavy, and basically they look like cross validation. So it's not just adding, but adding or combining or removing or just replacing or learning the features could help, but there are no guarantees. This is where machine learning goes from this sort of a heavily mathematical discipline into something that becomes more applied, something that is more of an engineering thing, where you have to kind of think about the problem and design a sweet spot solution. There is a certain amount of design aspect to that also. In terms of practical aspects, you have to think about overfitting with decision trees. We're going back to the decision tree. You have to think about overfitting. Decision trees tend to overfit if you grow the trees as big as they can get. So you have to deal with overfitting, and you could deal with it by, say, pruning the trees. You have to know how to deal with missing features, and in general, you have to think about when to use decision trees. You have to get a. This is something that you can build with by playing with different data sets. The general answer is, if your decision trees are going to get really large, maybe you might want to start considering a different algorithm. Um, there was a paper from 2007 or 8 by Rich Caruana, where the main lesson was, if you have a small learning problem, by small, at that time, it was like, if your number of features is less than 300 or so, and they're all discrete, then you can have at that time, the best classifier across many different data sets was not a single decision tree, but a collection of decision stumps, an aggregate, an ensemble. And if you have more, then you have to use a different system. What do you do is another question. What do you do if you have a very small and noisy data set in situations that occur rarely or are hard to measure? Yeah, this is unfortunately a common situation that we have to deal with. The easiest answer, of course, is to find more data, but that's probably easier said than done. I believe that in cases where the amount of data is very small, you need to think hard about the inductive bias that you're giving to the learning system. What do I mean by inductive bias? Inductive bias is, how are you constraining the learner so that it can easily find the solution? Any information that you give to the learner. There are two ways in which you can give information to the learner. One of them is by thinking about the problem and coming up with good features. The second one is restricting the hypothesis space enough so that there aren't too many options for the learner to search, because if your training set is really small, you're going to easily overfit it if you use a complex classifier. So you need to think about the problem and give it as much inductive bias as you can. Okay, switching gears from decision trees, we went to linear classifiers. You need to know what are linear classifiers. Basically, they are hyperplanes that separate the instance space or the feature space into two classes, two sides, positive and negative. They're interesting because many different functions are linearly separable, and more importantly, and I think this is perhaps the more important thing, the more useful side effect of linear classifiers is the algorithms that we invent with linear classifiers tend to be relatively easy to generalize to other kinds of things. So with respect to linear classifiers, you need to know what kind of functions they can express, what they cannot express. The classic example here, of course, is XOR. And you need to think about examples of functions that are linearly separable also. It is a very useful sort of a mental trick to understand the geometry of a linear classifier, because planes and lines are very well understood in geometry, which means we can borrow heavily from that perspective. When it comes to features, linear classifiers have a bias feature, bias term. So you have W transpose X plus B. I noticed that I tend to say W transpose X. Some people say W dot X, and some people write it as W comma X. It's the inner product. Use whichever notation works for you. But this term here is the bias. You need to understand what happens if we don't have a bias feature. If we don't have a bias feature, what we are doing is considering only those lines or those hyperplanes that go through the origin, which means we are restricting the kind of classifiers that we can build. And this tends to be something that's easy to forget. And even people who've been doing this for years might forget adding a bias feature and find that the classifier is just not working. So you need to understand the role of the bias feature, and also this trick that we saw where we could get rid of the bias feature, at least in notation, by moving it in, the bias term. We can get rid of the bias term in the notation by moving it into one of the features and adding an extra weight, moving a constant. So you have W transpose X plus B is exactly the same as W and let's say B transpose X and the number 1. Here, these things are vectors here. So now this whole thing can be W hat, and this whole thing can be X hat. And so now we are just left with the dot product of W hat transpose X. W hat transpose X hat. And it looks like in this higher dimensional space, if you have D weights here and a single number here, this vector is a D plus 1 dimensional object. In the D plus 1 dimensional object, we are now going to, we are considering planes that go through the origin. But that means in the D dimensional space, we are considering all possible planes. This is a useful trick that's just convenient for bookkeeping. There's a question, would it be equivalent to perform the right constant feature transformation across examples and not use a bias term? And is it equivalent to do that as using the bias term itself? If so, is there a reason to prefer one approach over the other? You have to be careful with this. You could possibly do that by basically essentially that would involve translating. If you have a hyperplane, if you have a line like this, that would involve moving the line around so that it goes through the origin, and you can do that, of course. That would involve moving the entire set of examples around. But the tricky thing is, how do you know how much to move? And why not just make it part of the learning problem? Why not just learn this expression and rather than a priori deciding on moving it around? So that's why I would prefer letting the learner take care of it. But yeah, essentially geometrically they are equivalent. Okay, so once we saw that, we just kind of went to our first of the many ways in which we ask the question, how good is your learner? This was mistake-bound learning or online learning. The general online learning is essentially a series of rounds, or you can think of it as a series of games between the learner and nature. The learner receives an example, and then it makes a current prediction. It reveals it makes the prediction using its current model. And then only after making the prediction does nature reveal the true label. And at that point, if there's a mistake, the learner gets to make an update. Then it tosses out that example, and then it goes back to the top. And this is just a general online algorithm. It's called online because it keeps receiving examples. I know this is an infinite loop that exists forever. Under this model of learning, this is just a mechanism in which learner and nature interact with each other. We looked at a formal definition of a mistake-bound algorithm, an algorithm that makes only a polynomial number of mistakes in the dimensionality. Such an algorithm may not exist. There may not be no such algorithm, but we proved that there is at least one such algorithm called halving, and you need to know how many mistakes they make, and you should be able to prove it. I think of halving as being analogous to binary search, and scorn as analogous to linear search. But if that analogy doesn't help you, you can ignore it. but you should be able to prove it. You should be able to use the result from halving on finite hypothesis classes. The important notion is the number of mistakes they make, halving makes, is log of the size of the hypothesis class. So let's call that h, which means the key thing that you need to be able to do is count the number of functions in the class, just like you're doing with this homework currently that you have. You're counting the number of functions, and then if the log of that is polynomial, life is good. You need to know some examples of functions, the hypothesis classes that are learnable under this model and that are not learnable under this model. An important class of functions that are learnable under the mistake bound model is linear classifiers, because we have a proof of concept. We have a proof by existence. The perceptron algorithm is a mistake bound algorithm that can learn linear classifiers. The algorithm is so simple. It essentially has the same 3 steps that all learning algorithms have, all online algorithms have. You receive an example. So let's say given an example X, and let's say that we are also given the label Y. You check if Y times W transpose X is, I'm assuming that the bias term is inside the example, is negative, then you have W is W plus RYX. This is the simplest version of the perceptron algorithm. There are many variants of this, but you should also understand the geometry of the perceptron update. The perceptron update involves, on a positive example, if this was a mistake, then what it would do is it would, let's say you have a point here, this is positive, the perceptron update would try to essentially rotate the line so that it becomes more like, it becomes closer to the hyperplane. And similarly on the negative side also, it rotates the line so that it becomes closer to the hyperplane, but on the other side. So it tries to, and we kind of saw a simple example of this. There are many variants of the perceptron algorithm. One of the good things about an algorithm as old as the perceptron is that it's so easy to, and as simple as the perceptron is, it's so easy to invent variants of these things. The 2 variants that we saw in some detail was the margin perceptron and the average perceptron. You should be able to implement them. A key technical concept that you need to understand is the notion of the margin of a classifier. We're going to revisit this when we talk about SVMs, because SVMs are there are some people who refer to support vector machines. SVM is support vector machine. There are some people who refer to support vector machines as max margin classifiers. The idea of learning is built around the margin of a classifier. The margin of a classifier is the distance of the closest data point to it, assuming that it has the right label. Let's say this is a plus, this is a plus. With respect to perceptrons, you need to know the Novikov theorem and its proof. Essentially, it says the number of mistakes is less than R square divided by gamma square. R is the radius of the data, and gamma is the margin of the data. Radius means if you have a bunch of examples, irrespective of what they're labeled, actually, you know what, let me, so if you have a bunch of examples, this is a linearly separable data set. The Novikov theorem only works for linearly separable data set. The excuse me, the radius of the data would be something like the radius of this circle, assuming that all these points are centered at the origin. And the margin of this data is the gap of the perfect classifier to the closest data point. You need to understand the intuition behind the algorithm. There's a really cool geometric intuition, and I encourage you to kind of think about that. And I also encourage you to think about how you would apply this proof if you had to not prove a mistake bound for the perceptron, but for something like the margin perceptron. Turns out the margin perceptron also has a mistake bound, and it's worth trying to prove the mistake bound, because that will force you to really grapple with the theorem. We also looked at least mean square regression. You need to know what is linear regression, what is least mean square regression. And more generally, the most the sort of the important idea from this module that we saw that we'll be carrying ahead is this idea of learning by minimizing a cost function. We wrote down, instead of actually inventing an algorithm, what we did was we said, here is a scenario that I don't like. I'm going to penalize every single weight vector for an example. For each example, it um, the penalty for that thing is the prediction it makes minus the ground truth, let's say yi squared. For the ith example gets this much penalty. The ground truth is yi, the prediction it makes is w transpose x. The weight vector w gets a penalty of the difference squared on this example, and on the entire data set, the weight vector gets a penalty of the sum. And now a reasonable strategy for learning is I want to find a weight vector that minimizes the penalty. So this thing here is the cost function, and I want to minimize that. This idea is actually a very productive one, and we will see this idea is going to be the basis of pretty much what is today considered as modern machine learning. We encountered it first in the context of linear regression, and in general for regression, this is the cost function that we use. We will encounter a whole bunch of other cost functions for classification tasks. In fact, we will see how the perceptron algorithm, not the online one, but the batch perceptron that you implemented in your homework, actually falls into this framework also. In particular, once you write down such an objective function, you can call upon any optimizer. You know, the field of numerical optimization is a rather robust one. We can call upon any optimizer. Today, perhaps the most uh, uh, prominent family of methods involves using the gradient of the function. And in particular, we saw this idea of stochastic gradient descent, which we will encounter again. And you need to know what's the difference between these things. Finally, we also looked at, most recently, we looked at computational learning theory. The driving assumption for PAC theory, probably approximately correct learning, is that training examples and every example in the future, the test examples including, are drawn from the same distribution. This is a assumption of convenience. We make this assumption because it makes it easy to prove things. Doesn't necessarily mean that this assumption is true, we just make it. You need to know what's the difference between the batch model for learning and an online model for learning. In a batch model for learning, you're given a collection of examples and the learning algorithm can do what it wants with it and it spits out a classifier. In an online model, there is this sort of series of rounds where the learning algorithm gets one example, has a model that it keeps updating as it goes along. In PAC learning, there are two factors that are important. One of them is how close will an approximation to the true concept be? This is the epsilon. We want epsilon to be small. We want to get as close an approximation as possible. And the other thing is how sure are we that the learning algorithm will find a hypothesis that is good enough? This is the delta. We want delta to be small. So the confidence in our learning is really 1 minus delta. So we want with certainty that the learning algorithm will succeed. And we define success as finding a good classifier, a classifier with low error. With these two parameters, with epsilon and delta, there's a formal definition of PAC learning. And also there's a formal definition of efficient PAC learning. The idea really is that the number of examples needed is polynomial in 1 over epsilon, 1 over delta, the dimensionality, and the size of the hypothesis space. And here, the time is polynomial in all the same things. If this can happen, if a concept class has a polynomial sample complexity, the number of examples needed, then it's PAC learnable. If a concept class has polynomial computational complexity, then it's efficiently PAC learnable. So there's a question, can I explain the difference between updating weights and an online model? Updating weights is in some sense an online model. The only difference is when we are updating weights, there is no assumption that after we update the weights, we throw away the example. In online learning, it's a rather strict restriction where you get an example, you make an update, and then you don't see that example again unless it accidentally comes back your way. So if we are setting up this game of updating weights, I can keep the weights in memory and just kind of iterate over it again and again. All of that would be batch. Will I be posting these slides on the class website? Yes, I will. There will be some place where with a lecture on practical advice that is supposed to happen at the end of the semester. This is part of that, so I will post it there. So using this definition of pack learning, we looked at Occam's razor for consistent learners, and once again, the key concept was we needed to count the size of the hypothesis class. This is the second time we are seeing this. We saw this for mistake-bound learning also. With this notion, okay, there's a question. If the requirement is yes, this is all in the context of finite hypothesis classes. We went to infinite hypothesis classes and noticed that the VC dimension behaves like the log of the size of the hypothesis class. So there's an interesting question. What's the relationship between mistake-bound model of learning and pack learning? The answer is any concept class that is learnable in the mistake-bound model is also learnable in the pack model. There's a formal, this is a formal statement. And in fact, there is this general technique, given an online algorithm, there's a general technique for inventing a batch algorithm. It's called online to batch conversion techniques. In fact, you may not have realized it, but you actually have already implemented one of those things. When we did the perceptron algorithm, the original perceptron algorithm was just online, right? It takes an example, makes an update, tosses out the example. But the minute you start running over a data set multiple times with multiple epochs, that's an online to batch conversion technique. The average perceptron, or the perceptron algorithm that you implemented for your homework, was a batch algorithm, because it took a data set, it did some processing over the data set and returned a classifier. That was a batch algorithm. And now it turns out that every mistake-bound model is also, every mistake-bound learnable concept is also pack learnable. So together, we have a theorem that says if something is mistake-bound learnable, it is pack learnable. And we have a technique for converting an online algorithm into a batch algorithm, or a mistake-bound algorithm into a batch algorithm efficiently, which involves iterating over the data many times. So there's a very strong relationship. How do we quantify the time for a potentially pack learnable algorithm? There are a few ways of doing this. One of them is actually to write down the algorithm. If you can write down an algorithm that can successfully learn, and you can show that it is polynomial, then you're done. Alternatively, the opposite side is you essentially show that if this thing was, basically you set up a reduction to an NP-hard thing. So you say that this is intractable. That requires a proof. That requires a proof that if this problem can be solved, then some other problem that's known to be hard can also be solved in polynomial time. We know that cannot be solved in polynomial time, so this must also be intractable. So that's the general statement of these kinds of proofs. We haven't seen any of those formal proofs, because that would be something that maybe you can see in an algorithms class, for example. So you need to know what kinds of concept classes are learnable and not learnable from the complexity perspective, both sample and computational, in the set of consistent learners with finite hypothesis classes. But then we quickly moved on to, we noticed that, the hypothesis class may not really contain the true function. So maybe it's hopeless to expect that a learner will find a classifier that's consistent with the data set. So, and it also seems rather naive to assume that we know the set of functions that nature is going to draw its true class from. So this is the setting that's called agnostic learning. The learner is agnostic to the true concept class. In this case, also, we proved an Occam's razor result using a different technique. You should be able to, both these proofs, this Occam's razor for consistent learners and the Occam's razor that used Hovding's bound, you should be able to work through the proof. And once again, the key notion here also was the log of the size of the hypothesis class, the key quantity that was worth computing. Now, that whole thing breaks down, as the question asked before, it breaks down if we have infinite hypothesis classes like linear classifiers. And in that case, we looked at shattering and VC dimension. VC dimension it behaves like this quantity here. And in fact, one of your homework questions in section 3 of the homework explicitly tells you to prove that if your concept class is finite, then the VC dimension is at most log of the size of the concept class. These two things are basic. The VC dimension is a generalization of this quantity here, but to infinite hypothesis spaces. So you should be able to, one useful thing that you should be able to do is compute the VC dimension of small hypothesis classes. There, it's not necessarily something that you will say use when you are, say, the director of technology for for Google, but it tends to be a useful party trick if you go to the kind of parties that I hang out in. Also, the other useful thing is more seriously, being able to compute the VC dimension of a concept class is going to take us to directly to, say, things like support vector machines, where we will see that the VC dimension has a certain relationship to generalization, and we will invent a learning algorithm that explicitly tries to minimize a certain quantity involving the VC dimension or maximize a certain quantity. And it provides the intellectual fodder for what comes next. Even though we may not be able to use, we won't use this directly. The other fun thing that the VC dimension proofs allow you to do is it allows you to think about the deficiencies of today's machine learning. So we have 2 minutes left, and I will, if there are no other questions, let me tell you an interesting thing. We're talking about pack learning and computational learning theory and all of this. What does this mean? That the theory of learning is solved? Does this mean that we have, in some sense, the laws of physics equivalent? Do we have general relativity for the role that general relativity does for, say, astronomy and cosmology? Do we have that for machine learning? The answer is absolutely not. In fact, one could argue that computational learning theory is deficient in a lot of this, in explaining why today's state-of-the-art models are actually working. Today's state-of-the-art models have VC dimensions that are humongous. They are in the millions, and yet they seem to be doing fantastically well, which means that the sample complexity should be large, extremely large, and yet it's not. So there is a mismatch between the theory of machine learning and empirical observations that are coming out now. So if any of you want to become rich and famous, you can start proving these theorems. There's another question. I'm confused about the log of the hypothesis space. If the concept class is infinite, we can no longer compute this quantity. If the concept class is infinite, we have to only deal with the VC dimension. The VC dimension in the theorems, in the sample complexity theorems, the VC dimension shows up in places that are analogous, not identical, to places where the log of size of h showed up. So it's so the VC dimension is like it's a complexity parameter. So there are 3 more questions, and I have no more time, so I will try to quickly go through them. And feel free to drop off if you want. If we use decision trees with MISC attributes, does that satisfy the 2 feature right? Yes, you're right. It does. So the total number of submissions is 5. No, it's not. It's 6. You still need to submit the 2 feature sets. you still need to make submissions. You can use 2 feature sets for any one learning algorithm. Yeah. If you want to intern in machine learning, what might an average interview consist of? Oh, wow. Okay, this is um, an interesting question, and maybe I'll reserve that for office hours if you don't mind. Is there a prize for winning the Kaggle competition? I haven't thought about that, but maybe there is. Let's say there's a. I haven't thought about that, and I'll talk to my TAs and ask them what they think, and if maybe I will create a prize. Why not? If you use decision trees with MISC and the perceptron with glove data, does that satisfy the 2 feature set requirement? Yes, it does. Yes, it does. It satisfies 2 feature sets, and these are 2 separate learning algorithms also. Okay, I will have to stop. I do have office hours in 15 minutes where we can continue this conversation or any other conversation you want. So please come by. And I know that I skipped over one of the questions about the intern, and I'll get back to you by email. Thanks.